Hi class, in this video what I want to do is go over the gas liquid chromatography, or more popularly called as the gas chromatography. So the acronym for that in that case would just be GC. So what is it about? The word chromatography comes from the study which includes separation on the basis of chroma, that means color. So it kind of stems back, if you have some background on chromatography in general, it kind of stems back to the fact when people in olden times were able to, or for the first time were able to, isolate the components of let's say chlorophyll A, chlorophyll B, xanthophyll, carotenoids. They could be separated from each other using a ground mixture of leaves. Or the way it was done was that you would take a piece of special filter paper, it's called a Wotton paper, and you would just load the mixture of crushed leaves, and then you would immerse this strip of paper in what is called as an eluent. And as the eluent rises, you would see the separation of the components. So now one could say that the number of components that are present in the mixture would be same as the number of bands that you're seeing. And the separation in that case was simply on the basis of solubility, on the basis of the ability of a certain component to move with the eluent. So for example, if two things were, let's say I had component A, component B, this is A, this is B, this is C, this is D, and this is, let's say, water is my eluent. And if A is showing up least, that basically tells you that A is not very soluble with water, because guess what? Water would be the one which travel fastest. So you can, looking at the distance that it had traveled, one would be able to make predictions in terms of solubility or vice versa. This is general chromatography that I'm talking about. There are various different kinds of chromatography, like column chromatography, high performance liquid chromatography, which is a very specialized tool in research these days. Of course, GC is what we are going to focus on. And TLC, thin layer chromatography. And those of you who have run in biology, if you've run a gel electrophoresis experiment before, it's kind of similar to that. The only difference being that in gel electrophoresis, essentially the separation is being done in presence of an electrical field. In this case, however, we are basically utilizing the ability of the solvent to carry the component with it. Sometimes it could just be gravity, under gravity, for example, in case of column chromatography, things of that nature. Hopefully that gives you an idea before we begin our discussion on GC. All right, let's go forward. So, what is GC used for? GC is basically used to separate and analyze compounds. I use the word analyze over here because GC is a technique which we can utilize in order to run samples which are really, really tiny. I mean, recall that episode from, let's say, CSI Miami or CSI whatever, New York, where they get a very little, very tiny piece of evidence, tiny sample, and they're still able to, detect the presence of a certain component that they are looking for. How do they do it? They do it because they are able to utilize techniques such as gas chromatography, which requires samples of the size in a micro or a nano range, and they are instruments that are so sensitive that you would be able to track down, you would be able identity of a certain component. In this case, the sample needs to be heated up. So if your sample is actually heat sensitive or temperature sensitive, you cannot expect this to be a non-invasive, a completely non-invasive technique. No, that won't be true in that case. The other thing that I would like to say is because you're heating the sample, lower is the boiling point, because you have to go from the liquid phase to the vapor phase. Lower is the boiling point. That would mean that those particular samples would be seen first. So the deal is that, let's say you have two components, and they're A and B. One of them boils at, let's say, 80 degrees. The other one boils at 180 degrees. So now when you inject the mixture together, you inject that into your column, you're going to see the vapors of the 80 degree, which is vapors of A, those are going to come in faster as compared to the vapors of B because it's just higher boiling. So when you get your chromatogram at the end of the day, so let's say your chromatogram looks like the retention time, and I'll talk about all that in a second. And here's your sensor, and you get two peaks. You can identify that the first peak is going to be for product A, second peak is going to be product B, and you're able to do that because the first sample is coming in first, and that also happens to have a lower boiling point. So what's the take-home message? The take-home message here is that in case of a GC, lower is the boiling point. That would mean that particular sample is going to go faster. Let's try to apply what we have learned from Organic 1 and try to predict on the basis of forces of interaction. Let's say A, let's give a face to this A. Suppose A is butane and B is butanol. And so now what do I know about butane and butanol? Well, if you look at the structure, you can hopefully predict that this particular one does not have any functionalities. And so the only things that you see are carbon and hydrogen. And what did I tell you about carbon and hydrogen containing compounds when you have only carbon and hydrogen? That those are greasy, those are non-polar. So the only force of interaction that you're going to see, that you're going to expect in this particular compound is going to be the London forces. What do I know about butanol? Hydrogen is bonded directly to oxygen. That automatically tells you that there is going to be hydrogen bonding. And the presence of a hydrogen bond tells you what? The presence of hydrogen bond tells you that it's going to be an extremely polar compound. And the reason for that is because the force of interaction that you see is very, very strong. And of course, because of that reason, you require greater amount of energy to break free from other molecules, and the boiling point is going to be higher. The boiling point here is going to be lower. So now that we have the two structures, we have information about forces of interaction, we just predicted for ourselves that the butane molecule is going to have a lower boiling point. So if I give you a chromatogram now with two peaks and I ask you which one is which, you would say, well, the first one, since we know that the boiling point is lower, and so the retention time should be lower as well. So the first peak corresponds to butane, the second peak corresponds to butanol. Hopefully that sounds good. So you would see that GC can be used to separate and analyze compounds, but in reality, actually it's used more for the analysis rather than the actual separation. There are much better tools to separate out components. Usually a GC is run to analyze and figure out how many components are present in a given reaction mixture. So like it says here, typical uses would basically be to test the purity of a sample. You know nothing about the sample. You can simply run it on the GC, and the number of peaks that you get is going to give you the total number of components that are present in your mixture. That's pretty pertinent. Number of peaks is going to be equal to number of components. And this is, of course, with an assumption that our component does not break down as you are heating. So it's not, you're seeing the number of peaks. It's not that the component is breaking in a continuous manner, sort of. And so, looking at the number of peaks, you can basically make assumptions about the forces of interaction or the boiling point if you have the chromatogram in front of you. All right, let's go forward and see if we can apply this information and learn more information about GC. You hopefully can envision that this technique is kind of similar to fractional distillation in some sense. And the reason that I say that is because you have a solid or a liquid sample. You can have a solid GC, by the way, but it's a solid or a liquid sample, and you're basically bringing it all the way to the vapor phase. So ultimately, it's the ability of a certain compound to go through the vaporization procedure, and then it's the vapors which are sent, which are moved, which are carried with the mobile phase of the chromatography, and the separation occurs on the basis of the boiling point, of course. So if I were to run, let's say, if I were to separate out, like I was saying earlier, if I were to separate out maybe, 20 milliliters of a given sample into its components, I would just do a fractional distillation for that matter. It's, it won't be that time consuming. It would not be that labor intensive. I will set up just once, and in about an hour and a half time, I would be able to separate all of my components out. On the other hand, if you have to figure out, well, how many of those components am I supposed to figure out, I will first take that reaction mixture, run it on a GC, see how many components I have, and take it from there. So if I'm not given any information, and I just have been given some liquid to work with, the first step should be just take a microliter of that, or maybe even less, and run a quick GC to see where your components are lying and how many such components are present before you start carrying out a full fractional distillation in order to separate those out on a large scale. Okay, so like I was saying earlier, every chromatography basically is composed of two phases, a mobile phase and a stationary phase. So recall the example that I was giving you when I was giving you some introduction, some background information on chromatography. And I gave you the example of the leaf mixture in which we used paper. We used our sample, and then we basically subjected that to elution. So water was my eluent, which moved through the paper. Paper was obviously static, stationary. It did not move. So what moves is the mobile phase. What does not move is the stationary phase. So one can say that the paper in that case was my stationary phase. In this case, in the gas chromatography, we inject the sample, we heat it up, and then we carry it with a inert carrier gas. So basically, you can see that you kind of blow in the column to move your components through. The gas that's usually used is helium, argon is used as well, nitrogen, and 2 is used as well. So these are some classical choices one could make for the mobile phase. My question to you is, okay, I understand helium, I understand argon. These are noble gases, and that's why probably we are using, because focus on the word, inert carrier gas. You don't want to inject the sample and then use a carrier gas like fluorine or oxygen, which is going to oxidize your compounds. You want to inject and you want to see the retention time. You want to get the properties of the same organic component. So you don't want your gas to be a reactive one. My question to you is, why nitrogen? What is so special in nitrogen that allows it to be used as a carrier gas? Any ideas? Well, if you're thinking along bonding, yes, then you are thinking along the correct. That's your Lewis structure for dinitrogen. Notice there are 3 bonds, so nitrogen is actually a very stable gas, and it won't go through a bond breakage, and it's not going to react with anything and everything. So that's the reason that nitrogen could be used, liquid nitrogen, not air, because air is 20% oxygen, so not air, but nitrogen, helium, or argon. It has to be inert in nature. And in our case, our stationary phase is going to be the column, which basically has a polymer support on which we inject our samples. So what was paper in case of paper chromatography now is going to be replaced with a polymer support, which is what the compounds are going to move through. Lots of words here, but what's happening is you have, let's say this is my column, and right now here it only looks maybe about 2.5 inches. In reality, GC columns could be as long as 30 meters. You're going to inject your sample, so let's say this is the starting point, and this is where it's going to be heated. And as it's heated, it gets converted into the vapor phase, and it's going to start moving through the column. And if you have 2 components, then they are going to move at different pace, because they are going to move. The speed is going to depend on the boiling point, and that is how you would be able to see the separation into 2 different peaks. And then what you get at the end of the day, looking at the 2 peaks, you would be able to analyze the chromatogram and make certain predictions about that reaction mixture. So again, couple of points. You need very little sample. Usually the amount of sample that you inject is 0.2 microliters only, so very, very tiny. The concentration is pretty low as well, and it's able to record a lot of times. In the lab, you might see that the lab tech would inject your sample and say, oh, I need to do it again because the system got saturated with the sample. What does that mean? That means that your sample is so much, there's too much sample in that particular injection, and that has now overloaded. The column cannot handle that amount of sample in a given time. So your peaks will start to look kind of like that rather than a nice tip on top. And so in that case, he would need to kind of go back, dilute your sample, and run it again. So that's what's done. But like I said, the temperature is a pretty important component too. If the temperature is not maintained, there is a possibility that one might miss one of the components. What I mean by that is, let's say you have a 3-component system. You have one that is at 80. There is another one that's at maybe 110. And there is a third one which is at 300. And you maintain your column at, let's say, 120 or 125, somewhere there. You would be able to see the first two. You may not be able to see the third one because the temperature is way too high. So even though you're using a carrier gas at a pretty good flow rate, you may not be able to see that last one because the boiling point is significantly higher in that case. So you would think that it's a 2-component mixture. In reality, however, it's 3-component mixture. So whenever a method is set up, usually they cover a range to run it several times to make sure that the number of components that you are seeing is the number of components you're supposed to see. So it's consistent over a range of various different temperatures. But what is detected is usually what comes out of this outstream. So what comes out here is what's detected by the detector. There is an animation that I have in one of these slides that we are going to watch so that we can see. It's in the PowerPoint, so it may not work on the PDF, but you can watch it on the PowerPoint for that. But like I said, the GC that you get at the end of the day, where you have your detector response, some people call it sensitivity, but that's the response that you're getting, and this is the retention time. So retention time is after how many minutes were you able to start seeing your sample, and let's say you get this kind of a GC, and you're supposed to tell what's what. So you can tell looking at this GC that it's a 3-component GC, where A supposedly would have the lowest boiling point and hence the minimum amount of forces of interaction. B will have the intermediary, the second highest boiling point, and then C will have the highest boiling point, highest BP, highest boiling point. And the other thing that you can determine from a GC is by determining the area under the curve. I still remember when I was an undergrad, in order to get to, figure out the area, we had to draw equal squares. So we would plot this on actually graphing paper and then count the number of squares. I'm surprised I didn't get, my eyesight didn't go bad after that. But what you want to do really is you want to determine the area under each of these peaks. So you cut right over here and over here. Good thing nowadays is the computer does it for you. So you just have to read from the report. It's as simple as that. And that will give you the amount of the compound that is present. So you can actually get a percentage of the composition for your given sample. So what that means is, let's say in this case, you can just simply eyeball that you probably have 80% of your sample is B, And then these two peaks are they about have the same amount, so you probably have 10 each for A and C. So one can say that A is to B is to C is in the ratio 10 is to 80 is to 10. And if you get the simple ratios, 1 is to 8 is to 1 is the percentage composition. You can say that in terms of amount. And if somebody says that you got a total of, let's say, 5 gram of the reaction mixture, and somebody asks you how much of that 5 grams is B, you would say, well, 8, since it's supposed to be 80%, then 0.8 times 5, 4 grams is going to be the percentage composition for that mixture. So this is just a general schematic for a GC where you can see where we are going to inject from. It goes through the 30 meter of the column, and of course the carrier gas at a certain flow is going to carry the vapors from vapors of the sample, and it's going to go through the column, and then we are going to see the detector response on the computer, and it's going to plot it, and that's what you're going to analyze. Now realize that if your samples are like way too close to each other, the sample components are way too close to each other, if your column is longer, it's going to separate better. So for instance, if your peak kind of looks like that is showing you that it's A. Look how kind of plateaued this part is. That's showing you that this is a saturated system. That means the amount of sample that was injected is too much. That's one thing. But notice that this area does not contain just one, but perhaps two peaks. And the reason I say that is because of this part. It looks like two peaks were sort of overlapping on each other. And so if you change the column and just make it longer, you might be able to see for a dilute sample, you might be able to see something like this, which clearly then will indicate the presence of two peaks which are really, really close to each other. And probably that just basically means that the boiling points are absolutely very close to each other, which is why they are nearly overlapping on top of each other. But if you have a longer column, of course, the separation would be a little bit better. Or you can simply reduce the sample size and you would still be able to see the separation on your column, because each column costs close to about $1,500 to $1,000. And so if you want to save on some green, another cheap alternative would be to just basically lower the concentration. But then keep in mind that if you're lowering the concentration and if it is a sample which has multiple components, you're actually lowering the components for all. So it's a possibility that some of your peaks might just kind of look like that rather than a nice peak. So you have to be, it's a which way you go. This was the slide that I was talking about, and since this is a PDF, it won't work over here, but you can actually run this on the PowerPoint on Blackboard. So this is where you would inject, and we have nonane and decane. So there's two components that would be injected over here. They're going to interact with the column, and then they're going to come out of the column and be detected. So you would see you have one which is nonane, so that's a C9, and then decane, which is a C10. So hopefully you can see that C9 is going to be the one which will have a lower retention point because it has less number of carbon atoms. So that's the peak that you expect first, and then C10 is going to follow along later because you expect the boiling point to be higher in that case. And of course, if you are able to measure the percentage that's under each curve, under each peak, you would be able to figure out the percentage composition for the given mixture. And this is actually the actual GC that we have. So notice this tube right over here. That's the column that I have been referring. So it is actually pretty long, but it goes pretty fast. Each GC run usually takes close to about 2 minutes or so, because you're dealing with vapors. It goes pretty fast. Alright, so some of the variables that you can change, of course, the temperature of the column, the inlet, the detector, type of carrier gas. You can keep it helium or argon or nitrogen as long as it is inert. That is what we are focused on. But of course, the rate at which it moves, so the flow rate, is going to be important. You don't want to go at a flow rate which is so high that it basically blows over anything and everything that's on the column. So that's like a little hurricane there. It has to be sort of like a gentle breeze, which is carrying the vapors with it. So it's just aiding it. It's not going to carry anything and everything that's on your stationary phase. And of course, the diameter and the length of the column, that is pertinent. You have to maintain a certain ratio, and there is no fixed number to go by. It actually depends on your sample. One has to run it several times to be able to see, and of course the sample size, you want to keep that to a minimal if it's an analytical GC that we are after. Okay, let's see if we are able to apply what we have heard in the last 20-25 minutes or so. You're given a detector response. This is the retention time, and I'm giving you some information about 3 components that you have: butanol, butanal, and butanone. You have to label which one is which. So for the sake of argument, let's maybe say this is A, this is B, and this is C, so I don't have to write the complete name. Notice the molar masses of these are pretty close, so you expect, technically, oh, molar mass is same. Maybe the boiling points are going to be same as well, but guess what? It's not. The reason why it's not is because the structures are different. So recall from organic 1 that it's not just the molar mass, but rather the structure of the component which decides the polarity and hence the forces of interaction. So butanol, for example, it's 1 butanol over here, so that's this molecule. Butanal is this molecule. Butanone is this molecule. So those are the 3 things. And notice that the 3 boiling points are 118, almost 75 and 80. And we have to predict what's where. So hopefully you can see that the lower is the boiling point. That is the one that should go first. So it should be B over here. You should have A over here, and you should have C over here. And now that you have identified which peak is where, you can perhaps eyeball that about 50% of the reaction mixture is C, and the remaining is divided into B and A. So if somebody asks you what's the ratio of B to C to A, you will have to get the ratio from the report and figure out a simple ratio by dividing by the smallest of all the numbers and take it from there. So again, you can, by looking at the number of peaks, you're figuring out the number of components. By looking at the area under the peak, you're determining the amount of the material, which is the percentage composition. And you can use that to your benefit. If you have grams of yield that you generated for that particular sample, you can actually figure out the particular compound that you were interested in, how much of that sample it is, provided you have, of course, identified identified the correct peak. What else? You can also go vice versa. If no information, about the boiling point or the structure was given, then you would say, well, the first one is supposed to have the least number of forces of interaction, or least strong, weakest forces of interaction. On the other hand, A should have the strongest forces of interaction. You can say that for sure. Okay, I think that'll be all for GC, and hopefully you would be able to apply that for the forthcoming problems.